All right, so so I started a project called Filecoin Green, which has focused so far on connecting Filecoin to renewable energy and doing that in a way that's publicly verifiable. But what I'm going to talk about now is a bit broader about how we should think about data provenance in sustainability claims. And so what I'm going to walk through is talk about why we need new tools for impact evaluation. I don't know if we could like turn down the ringing a little bit. I don't know if everyone else hears that. So I'm going to talk about why we need new tools for impact evaluation in especially the sustainability space. So things like renewable energy and carbon, why the tools that we have right now just don't cut it for allowing us to make claims that people can then audit. I'm going to talk about transform.storage, which is a set of tools that we've built in order to try to solve some of these problems. I'm going to talk a little bit about how you can take transform.storage and these tools and start implementing them in your projects. And then I'm going to give you a chance to use them to try and decarbonize your travel to FtC for free. So you can test them out. So regenerative finance, right, which is this whole area around building new tools in Web3 in order to solve environmental problems, relies on real world claims, right? So this is true in if you're minting carbon offsets, if you're allowing people to audit carbon offsets, if you're buying renewable energy and matching that renewable energy to your energy consumption, real world claims that I'm thinking of are things like the following, right? Claiming that my trip to FtC is net zero. Claiming that our power bill last month was 85 kilowatt hours, and therefore we've bought enough renewable energy to cover that. Claiming that our regenerative farm sequestered however many tons of carbon dioxide equivalent, or that we recycled e-waste, right? These are all claims about the real world, and we need tools to validate that these claims are actually true. The tools that we have in Web3 aren't super well placed in order to allow us to validate that the data that we are being given actually reflects the facts on the ground, right? So this is not like ownership, right? We need off-chain data. It's not as simple as validating ownership of an NFT. It's not like price, right? A distributed oracle is not actually a great way to validate that my power bill last month was 85 kilowatt hours, because that power bill comes from one source, right? That information isn't all over the economy. Asking 100 people to vote on what the value of my power bill was last month is crazy. It's not like state, right? You're not going to be able to pay enough gas fees to actually do the compute over data required to validate a lot of these claims going from raw data to your real world claims, your RWC. It's not like identity. We need identity, but it doesn't get us all the way there. The fact that someone is willing to pay a certain amount for a data set doesn't validate that that data set is true, right? So we can't just say markets for data are gonna solve this problem. It's kind of the reverse, right? People wanna know if data is correct before they know how much they're gonna pay for it. It's not like decentralized physical infrastructure. We don't wanna wait for people to have to build new consensus mechanisms every time we need a new data source, and it's not uniform, right? You might make a claim, like a net zero claim, that requires data from tons of different sources that's validated in tons of different ways, and we need all of those ways to be interoperable with each other. Right, so we talk a lot about verifiability in Web3, but how do we actually build tools that give us the verifiability that is most crucial for claims about the real world, which is that the data that we have matches the facts that are actually on the ground, right? This is clearly a lot to do with sustainability, but it's also to do with impact evaluation just across everything that we're talking about here, across funding the commons, across evaluating impact in our public goods programs. And so, we think about this in the following way. Here's the big bait and switch of this talk, right? I pull you in with sustainability, and it's actually about category theory. So we think about this in terms of these compute diagrams, right? So the way to read these compute diagrams is that data comes in from the left and goes out through the right. You may have a line, right? So a line just means data goes through that square and it's unchanged. If you're doing some sort of transformation to that data, we're gonna label that as a box. We're gonna use these functions to model either functions that are reproducible or functions that maybe are state dependent, that depend on some external real world state, or even transformations that just happen totally offline, right? You might have auditors, you might have people following a spec and going through and doing something with data that you don't necessarily expect to be 100% reproducible, right? We're just gonna model all those data transformations with boxes and hope that they commute. Then you could also have, functions with multiple outputs. Functions also can compose. So if the data type of the output of one function matches the data type of the input of the next function, we're going to draw the boxes next to each other and say you do transformation F and then transformation J. So, okay, so why is this useful for RWCs, and why does Web3 add something to this model and this way of tracking how information is transformed that's useful for real-world claims that you really don't get if you just use Web2 tools? Well, so RWCs are traceable and profoundly, deeply interoperable if you anchor them in content-addressed typed data. So what I mean by this is that if you're storing this data, so again, these compute diagrams, right? Boxes are functions or transformations, and lines are data, right? If you anchor your data in content addresses, then it doesn't matter where you store that data, right? You could store it on some Web3 platform, you could store it on a Web2 platform, you can store it on your own computer. You can verify that the data is indeed the data that is referenced by that line, right? And then if you make that data typed, and you make these transformations map between content-addressed typed data, then that same thing is true for computing over that data. So you can do that computation in a decentralized compute over data platform, you can do it on your own computer, you can do it on the cloud, and you can verify that this computational diagram actually maps to the data that the person who made it has in mind, right? So anchor your RWCs in content-addressed typed data, and then we can track data transformations that happen in many different places and are verified in many different ways. So maybe some data is transformed actually, on chain. Maybe other data is transformed in Bacalhau, a compute over data platform. Maybe other data is transformed on AWS. Maybe I'm running some transformations myself, right? Maybe some transformations are done literally by hand, right? A consultant is writing things on paper. It's fine, right? We can take that data, we can content address it, we can plug it into one of these compute diagrams and be confident that we are referencing the data that the person who made it actually has in mind. So, an example of this is a green score. So we've put a ton of work into trying to understand the environmental properties of different nodes in the Filecoin network. We've given them the ability to submit proofs of their energy consumption and their renewable energy consumption to an external party. We have those validation results. We also take proofs from the Filecoin chain on how much data is being stored and how much data is being onboarded, and can estimate the amount of energy used by a storage provider using that information, and we output this into a green score. So what does that look like in terms of one of these compute diagrams? You have these two different data sources coming in, one from the chain, one from this energy validation process. You transform this with this energy estimation function, and then you do this green score calculation, and the output is a green score, right? So that's an example of one of these computational diagrams. And so, how does transform.storage actually let you do this? Transform.storage, if you go to it now, it'll redirect to CO2.storage, which is the current sort of prototype of these tools. So we take these compute diagrams and we say, okay, useful data that we want to make claims and understand who we have to trust in order to trust these claims. That useful data has three different layers, right? There's assets, there's the raw data that's being pumped through these compute pipelines, there's functions that are actually doing these transformations, and then there's provenance of all of this, right? There's provenance of individual pieces of data, there's provenance of functions that transform that data. You might be interested in who actually wrote the code to do this, and there's provenance associated with compute. Maybe you have some zero-knowledge platform that you're using to run your compute. You can prove that this input data run by this function actually gives you this output data. That's great. That's one type of verifiability. Maybe your data and the program is totally public and you can just reproduce that yourself. That's great. That's another type of verifiability. Maybe you really trust the person who actually did this compute. And that's another type of verifiability, right? And real world claims rely on interoperability between these different types of verifiability, right? So we have these three different layers. We express those layers as compute diagrams. So here's on the left a really simple compute diagram where we have a single function that's taking a single input and giving a single output, right? So we have these three layers of that compute diagram. We have the assets, we have the function, we have the provenance information. So we're just going to explore the data model of this pretty quickly. The function itself has an input and it has an output. Those are typed. That's sort of the basis of these entire compute diagrams. Those types have schemas, and if you actually want to put data through this function, you have assets, right? You have instances of those types that are your input data and your output data. Then all of this, like I just said, has provenance information associated with it. So someone has signed this asset and said, I attest that this data is true, which you're going to do in a couple minutes if you want to decarbonize your travel to FtC. And someone signed that function and said, I wrote this function. You can take all this and wrap it up, roll it up into a single CID with what we're calling a data pipeline, which is a set of functions in one of these compute diagrams that says, okay, when I put this data in, I get this other data out. All of that, again, is anchored in these content-addressed types. So great. If you want more information on sort of how we're thinking about this paper is a work in progress. It's a few pages long right now. It doesn't have the data models in it yet, but it will pretty soon. This is a reference for that. Or you can go to provenanceprotocol.io, and that will redirect to this paper. I'm not gonna dwell on this too much. Also, if you want these slides, you can get them in the QR code that should persist at the top right corner. So what can I use this for right now in my project? Like if I wanted to use this today, right? Say I have a carbon offset project and I'm taking data in from 20 different people that I work with who are actually doing work on the ground, and they each have a phone, they're giving me useful data. How could I take that data, tag it with relevant provenance information, and plug it into one of these compute platforms? So these are the things that are implemented, documented, and also have a UI at co2.storage. The pipelines and functions, actually, as of like literally today, there is a section at co2.storage where you can go and start to explore these things. But the tools for creating types, creating assets, and then tagging all of that with provenance are pretty mature. And so I'm going to walk through just really quickly how you can use those. I've been hammering on about content-addressed typed data. So you can just go to co2.storage. You can enter in a data schema saying, okay, these people working on this particular project on the ground, they're collecting plastic. Here's the properties I need to know about that plastic. Or they're doing regenerative farming. Here's the stuff I need from them if they're going to contribute useful data to my project about their regenerative farm. Right, so you can just type that in, or you can import your own JSON schema using the API, and then you can take the CID of that type, and you can just go to form.co2.storage/that CID, and that'll make a form that looks like a Google form. People can open it using either Brave, if they have their Brave wallet set up, or using the MetaMask browser. More wallets will be supported soon. And they can just enter in all of that information just like they're using a Google form. But when they hit submit, they can sign that with their wallet. And then you have that provenance information tagging those assets. And you've already defined that type. All of the different pieces of this are content addressed. So their data contains auditable provenance information attesting to their impact, right? So, other things that are coming are data pipelines, private data. The ability to monetize your data and code is going to be super useful, and things like impact evaluation as a service, right? What pieces of this can we make modular and use that to supercharge public goods funding projects, public goods type projects all over the world. So I think we have a couple more minutes. I think this will work. So if you have your Brave wallet set up, or if you have MetaMask on your phone, you can go to one of these QR codes. This should just redirect to decarbonize.travel, I think. So that's another way to get to it. You can enter in your name, the event, something like FtC and side events. You can say the start date of when you're doing this trip, the end date of this trip. Give a short description of your travel. You can use the same thing for travel and emissions, and then do the one-way driving distance and one-way flying distance, right? So From Seattle, it was about 5,500 miles that I flew to get here, and I drove 10 miles or 20 miles or something to get to the airport. You can then, so that took I think about 1.5 tons of CO2, something like that. So you can sort of estimate that amount. It's okay to overestimate it a little bit. Don't overestimate it by like 10x. If you're coming from Europe or somewhere like nearby, like 1 ton should be okay. If you're coming from roughly the other side of the world, it should be something like 2 tons. If it's a lot more than that, then you're probably traveling in some wild, unsustainable way. Please, you can leave the offset transaction hash blank. When you hit submit, the asset will be created, right? So you're signing the input data into this compute pipeline. It's going to run on Bacalhau, which does distributed compute. It's going to go to the regen network. It's going to retire an offset for you and put your description in the reason for retiring that offset. It's then going to add the transaction hash to this asset. You're going to sign it, and then it's going to give you this output pipeline, which then if you go to co2.storage and explore pipelines, you can look at all the different provenance information associated with these different steps. Hopefully it works. It might take a little bit if the internet's kind of slow. But that's it. Thank you for coming, and happy to talk about data provenance.